Hello everyone. So today we'll be covering the topic how suffix tree can be constructed in just the linear time. So the suffix tree is used to solve many problems, and one such problem is longest substring problem, where you're given two strings S1 and S2. Uh, okay, here S1 and S2, where let's say S1 is ABCD XYZ and S2 is XYZ ABCD. So we have two common substrings. One is XYZ and one is ABCD, and the longest is ABCD. So we have written this. So this is the problem called longest substring problem, and this can be solved using suffix tree. So before we uh, get to the problem, let's understand what exactly the suffix tree is. So suffix tree is the tree which store all the suffixes. Let's say our string was XYZ, uh, XYZ X dollar. So here we want all the strings are given here. All the suffixes are given here, like starting from the 0, you get XYZ X dollar. Starting from 1, you get YZ X dollar. Starting from 2, Z X dollar, and so on. So basically, we are storing all the suffixes in a tree in such a way that if there is some common part among suffix, then that common part should lie on the same edge. For example, like here X dollar and XYZ X dollar have the first character X common, so that's why that part lies over here in uh, on common edge. So this is the way we have to construct the suffix tree. And once suffix tree is constructed, we can easily solve this problem by, um, if we take this example. So let's say we had two strings. I've taken smaller strings for demonstration purpose, ABCD dollar and BCX dollars. Now we have written BC because that's the longest common substring. So we have created suffix tree. Uh, how to create, I'll get into that part, but let's say that we have already created suffix tree, and the starting from first character, the suffix is abcd $b6 hash. So we'll create the suffix tree for the concatenated string of s1 plus s2. So it's like s1 and then s2. So starting from the first character, this is the suffix, then we get second over here. Okay, yeah. So we have to read it like this. So we get BCD dollar BCX pound. Okay. So once this is created, we can just look for a node which has both dollar and pound uh, leaves inside that. So basically, if we look at this node, this on this side we have a pound. On this side we have both dollar and pound. But in case we have both on a single path, we'll just consider the first character. Okay, so we'll say that this is dollar part. Now this node will has both dollar and pound, um, both below it. So any path before that node will be considered as common. So here we get C because C was common, and similarly, we get over on this node we get both hash here and pound here. So we get common as BC, and then we can compare the length of those strings and return the BC as our output. Okay, so this is how we solve the problem of longest common substring from suffix tree. But the scope of this video is not solving out the problem, but it's about the construction. So let's focus on that. So first we'll try to implement uh, or construct suffix tree in normal way, and then we'll try to optimize it. Okay. So there are three rules while constructing suffix tree. Rule one is if you reach end of the path, then we can add the character in the end to extend the path. Rule two is if there is no path exists, then we can create a new one using a separate edge. And rule three will I will show you in the example itself. Okay, so let's say we started with the node. We'll be taking the exact same string XYZ X dollar. We'll try to convert this. So let's say on our we'll keep two pointers I and J. Okay, and every time we'll look for the path from J to I. y. So I'll keep the present values over here. We'll set first to both to 0. So basically, I'm looking for a path from x to x. So my root node is blank right now, so there's no path. So using rule 2, I'll create a separate edge with path x. Okay. So now I'll increment the I by 1. So I is now 1 and j is 0. Now I'm looking for the path xy. So from root node, first I'll see whether I have path to x. So yes, I had it. So I'll follow this path again, but there was no y. So I have reached the end of the path and I'll add extra character over here. Okay, so I have added this using rule 1 extension. Okay. Now again, I'll increment j by 1. Now I have both I and j1, and now I'm looking for y path on. I'll sit on the root node again and look for the y path from starting from the root, which is not there. So using root extension, I'll create another edge with y path. Similarly, I'll this is a naive approach, so I'll just run through it. Next, we get a z, and first I look for xyz. I'll use rule 1 extension over here. Then again, I'll look for yz. I'll use rule 1 extension over here. Then using rule 2, I'll put a new branch from root pointing to z. Then again, okay, now this part is a bit critical. When I increment it again, my I will point to this and j will point to this. So now I'm looking for xyzx. First, I'll just add the character in the end. So basically, I've created all the suffixes xyzx, yzx, and cx. Now, for the single character x, I'll sit on the root node and look for the x path, which is already here. So this is the rule 3 expansion. So basically, if I have already found the path, so I can do nothing and move to the next iteration and keep on plotting the next part. So I'll move to the dollar section. So if I complete this tree, this tree will look exactly like this. So this is how we create the suffix tree, but the time complexity of this suffix tree is very large because I'm doing n iterations and in n phases, and in every phase I am doing n square operations. So basically, it's O of n cube complexity, which is way worse. Okay. But let's say there's a bit strange behavior that I'm doing. Like for every string, I'm putting dollar in the end or pound in the end. So that is because of this rule 3 expansion. Because see, if my last character was just x and there was no dollar, then the last suffix x would have ended in between, and it would not have propagated to the leaves. Okay, so this type of suffix tree is called implicit suffix tree, and we cannot solve problems using that. So to make sure that last character is unique, we add extra characters like dollar, pound, star, something like that, so that once dollar the dollar will come over here, it will come over here, and basically we get explicit suffix tree. Okay, so let's try to optimize it. Okay. Okay, so first optimization is edge level compression. Rather than storing the complete path, like for some path we were storing xyzx. Now this is a huge path to go on, and we have to traverse it at some time. Okay, rather what we can do is if our string was this and we just want to store this, we can store the start index and the end index is 0, 1, 2, and 3. So 0 and 3. This type of compression is inspired from impulsive compression. So the first optimization will be that we'll be storing the ranges. And second is if you observe the behavior for every character that comes. So let's say till now we had three suffixes x, y, z, and then we had yz, and then we had z, and a new character came in. like X. Okay, so the previous suffixes will also get appended with that character X, right? Here, here, and here. So why to travel every time to the each and every leaves and append that character? What we can do is, while storing the value of this, let's say it was 0 comma 2, it was earlier it was 0 comma 2, this was 1 comma 2, this was 2 comma 2. What we can do is we can store a different um, and we can store it in a different way, like 0 comma end. So this will be a global end variable, and I'll be just incrementing end whenever there's a new character coming in. So let's say my earlier xyz was getting stored in 0 comma end, where end was pointing and equals to 2. So it was pointing to xyz. When the next character came in, I incremented the end, and the end becomes 3 from 2. So now this is 0 to 3, which is nothing but xyzx. So this is just a simple optimization that we can do to make sure that we can append each character, each of the path with the newest character in just O of 1 time. Third part is suffix link. Okay, so if you observe this again, I had xyz. So starting from the root node. So I was also having YZ starting from the root node. Okay, so this behavior can be quickly traversed through suffix links. So suffix links say if there is a node which has path xy where x is a single character and y can be a string from with length 0 or more, then there will always exist another node where the path is y. So for xyz, basically x was okay. I should have taken another variable. Let's say a and b. So our x was a and yz was b. Okay, so there was another node pointing to yz. This node. Okay. Uh, so basically, while we are doing each phase, we should not be in requirement that travel or search each and every edge around some node to find where exactly we should go and append the newest character. Okay, so that part will be handled by suffix link. So this is the same for this part is same what I explained for every internal node u with path xy where x is interpreter and y is a string length 0 more, there exists another node v with path y. So we'll add a suffix link, this part. We'll add a suffix link from v to u. Okay. Concept of active points. Okay, so next optimization is related to bookkeeping because as we are trying to pull down our complexity, we will be doing bookkeeping a lot. So once a previous phase and a new phase start, we have to keep some of the state of variables from previous phase so that we can directly start from where we left off. So that part is handled in active points. So the concept of active points is to able to pause and resume across the phases. So let's say you had let's say you have some, okay, this was your root, this was your another node, you had some xyz string over here, you had some mn over here, and mxy here. Okay, now let's say you wanted to start from y point in your next phase. So what you can do is you can set your active node to root. So active node root and active edge is the x. In the real implementation, we will be storing the index of that x path, but for readability purpose, let's say active edge is x. Okay, and the node is root, and length is how much to travel on that path, which is 1. So basically, we'll stand on the active node, which is root over here. We'll out of multiple paths, we'll select the path that is starting from x. So that is this path, and on this path, we'll be traveling by 1 length. So then our pointer will be pointing to y. So this is the concept of active points where we can store the state. Okay, so when active length is 0, these are some of the rules. So When active length is zero, start the next phrase or iteration from the root node, which is like uh, very much sensible, because there's no length. You will not be traveling. Then you will be using the default case. If active length is non-zero, then obviously select the active node, select the active edge, and move on that active edge by the length given. Okay. There will be some very small change in rule 3, because earlier we used to do nothing, so we have to do something if we are trying to optimize it. Okay. So now what we'll be doing is we'll terminate that step, that phase, but will increment the active length by 1. Okay, so this is the change in rule 3 part. And okay, the last point I'll explain when we're taking the example. Okay, so now we have discussed all our optimizations. So let's start with the suffix tree construction. Okay. Okay, so this is our string that we are trying to create suffix tree for. So XYZ, XYA, XYZ dollar. Dollar is added by us in the end, so that our tree is a explicit suffix tree. Okay. Now we'll try to create this. So I'll explain the bookkeeping variables first. Remaining is the number of suffixes that are still pending to be uh, implemented or constructed in the suffix tree. Active node, edge, and length I already explained while explaining active points, and n is our global end variable that will be incrementing by 1 whenever the new character comes in, so that each and every suffix that was created earlier is already handled. Okay, so let's start. Okay, so these are the default values, and presently our suffix tree is blank, so end is -1. Active node is root, edge and length doesn't matter, 0, and -1 remaining is 0. When the first character x is coming, we'll first increase the remaining by 1. So now we have one suffix to be added, and we'll make this 0. So whenever we'll be storing 0, 0, it will be automatically pointing to x. Okay. So okay, so let's say this is our root node, and we sat on our root node, and we saw that whether or not we have a path connected with starting with x. We did not, so we will create a new node using our rule 2 expansion. Okay, x, it will be 0 comma end. Now, in normal, in actual algorithm, in actual implementation, we'll be storing the indexes, but for readability purpose, I'll just be showing you the characters. Okay. Okay. So now we have added this XPath. So I'll change this remaining to 0 back to 0, and our first phase is ended. Now the second character y will be coming in. Now y has come. Uh, I'll increment the remaining by 1. My remaining again becomes 1. Now active node is still root. We'll check, but before let's just add 1 in the global end variable. Now this is pointing to this is 0 comma end. As I've incremented end, this will automatically become xy, and I just have to add whatever is to be done with the new character. Okay, so I'll sit on the root node, look for y path. There wasn't any, so I'll just add 1y. Okay. um, okay, so now uh, I've added path. I'll again decrement the remaining, and my phase has ended. Next part z will be coming in. When z is coming, remaining becomes 1, end becomes 2. Again, adding end becomes 2. So this 0 comma end will become xyz, and this 1 comma end becomes yz. Okay. Now I'll have to add the z variable. So let's add the extra path z, which is like 2 comma end. Okay. Yeah, till now it was very much similar to what we did earlier. Now our actual bookkeeping starts from the next phase where we have received X. So this was still 0, this was still -1, this was still root. Okay. Now X came in. I'll add 1 in the remaining. I forgot to tell you that in a previous phase, when we created this Z path, I will also decrement the remaining because we created one suffix. Okay. Now for the next phase, I'll be incrementing the remaining again, incrementing the end variable again. So this will automatically become this. Okay. Now, uh, okay. Uh, Now I'll sit on the root node and see whether I have some path starting with X. So here on this path, my first character was X. So this is our root 3 expansion. Earlier we used to do nothing, but now for optimization, what we'll be doing is we'll be incrementing this by 1, active length by 1. Okay, and end the phase. Okay, so this phase is now ended. My next value is coming Y. Again, increment the remaining by 1. Uh, so earlier remaining was 1. It did not decremented to 0 because we did not created any suffix. Okay, so I've incremented this to 2 now, and my end becomes 4. When end becomes 4, this will automatically be handled. Okay, Y gets appended to all the leaves, and uh, my active length was 1. Okay, so now I'll sit on the root node. Okay. I'll say, okay, just a minute. Uh, I missed one part actually. In our previous phase, when we incremented the length, I must have also updated this active edge part because edge is still -1, so I'll update that to 0 because where I stopped my last phase at this location, right? So I have to store that in active point. So my active node is still root, and my edge is 0. 0 means is index. So index 0 is X path. So this path and active length 1. So I stopped at this location. Okay. Now in this in the next phase, I'll start from here itself, and from here I'll look for a Y. I have found Y over here. So here I found Y. So what I'll do is I'll increment the active length again. Uh, Now it becomes 2. This is still same, and my phase is ended. Okay. Now A will come in. Okay. Uh, first increase the remaining, then increase the end variable. This will become, all the leaves will become this. Okay. Now I have to start at location Y because I left at that location. I'll search for A, uh, but there's no A over here, so I have to implement a new internal node over here like this, which will point into A. When I do that, what I'll do is I'll decrease the remaining to 2. Now I did that, and I'll decrement the remaining length to 1. And my uh, I have decremented the active length to by 1, and I'll increase the active length by 1, so it will become 1. So now what will happen is because after Y I need a branch for A, and I need to know from where in the whole suffix tree where are the different locations from where I need to take out the branch A. Okay. So when I did this increment, what actually happened was starting from root node, I changed the branch. Okay. Earlier, it used to go this way because branch was selected, edge select was 0, and now I've implemented it, so it becomes 1. Now it will be traveling towards this one. Okay. So active length was 1. So again, what I'll do is select the active node, which is root, travel in the direction of 1, which is y, and travel by location length 1. So it will reach here. And once I'm here, I'll still again look for A, and which is not found. So I'll create another branch over here with A. Okay. So once I have created that, again, what I'll do is I'll first remove one remaining part because I've created one branch. Now active length will become 0. Now, as I said that when active length is 0, yeah, yeah, when active length is 0, start the next phase from root node. So from root node, I'll look for the suffix a or path a, which is not there. So I'll create another new path from here, which will be pointing to a, and my remaining will become 0 over here. Okay, and this phase will end because remaining is 0 now. We'll move to the next phase. Next three phases are very similar again. So uh, let's glide through them. X will come in, and remaining will go to 1. Remaining will go to 1 and will become 6. It will automatically be pointing to X, 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 all everywhere X. Here X. Okay, and then I'll sit on the root node and look for the X path, which is already there. So I'll just make sure that I update active edge and length. So active edge move into a direction of X and move by one length and terminate the phase. I haven't created this last suffix, so remaining is still 1. Y will come in. Y will start from the exact same location. This, and it will go to one more to one side, and remaining is 2. This will become 7. It will start from the location X. It will start from this location. It will move to in y direction for one length, and it will stop. So my active edge still is 0, and active length is 2. So basically, from root node, I have to select path 0, which is X, and move in that direction by the count 2. So I'll again stop this phase, and new phase will start at Z. Sorry, when Z comes in, not at start at Z. Okay. Now remaining is 3 and end is 8, and my starting point is this Y. I have found again the Z part, but the difference is I cannot just increment active length and move to next phase because there's an internal node over here. I'm jumping this node. Okay, so I'll change that. Okay, let's name that node to M. Earlier when it was created, it was M. Okay, so I'll update that active node to M. See this part. Yeah, this part I'm explaining. In case we jump over some internal node, we have to reset all three: active node, active edge, and active length. Okay, so I have to point this Z. So my start node will be M, active edge will be in the direction of Z. In the direction of Z means index 0, 1, and 2. So index will active edge will become 2, and active length will become 1. Okay, and then I can end this phase. Now dollar will come in. Dollar, there's a four remaining now. 4 suffixes are still remaining, and now we'll create suffix links. Okay, uh, over here. So let's just clean it a bit. Uh, okay, just a minute. Okay. Okay. So when we created these node, okay, suffix. Okay, this node was created in phase when A came in. Both these two nodes were created in this. So whenever any internal node is created, we have to point it to some node. If there is no pointer available, we'll point it to directly to root node. And if pointers available, we'll point to that node. So how do we decide the destination point? If in a single phase multiple nodes are created, then previous node will always point to the next node. So we had created these m and n internal nodes when A came in, because see here we had extra branch of A and here we have extra branch of A. So my suffix links will be like going from m to n. And why is that? Because whenever I might need to change this part, anything which is after okay, here I have x and y. Okay. Whenever I need to change something which is after y, then I'll have to also go to node n to change that part. Okay. So this is the suffix link bookkeeping. And now dollar when dollar is coming, we have a remaining 4 and end is 9. And our start node is different than root node. It's m node. We're starting from m node in direction 2 and length 1. So we'll be starting from this z. Okay. From this z, we'll first search for $sign. Is there any dollar or not? There wasn't any dollar over here, so we'll just create an extra node over here. Let's call it O. Hmm. And we'll create this. And first, we'll point this to root node. Uh, suffix link will point to root node. And if in this present phase I am creating any new nodes, new internal nodes, I'll have to point that over there. Okay. Now once I have done this, so I'll check my okay, I'll do no change in active edge and active length. I'll just travel the suffix link of active node. So from active node M, I'll I'll just travel this line and go to N and change my uh, it was M earlier and I have changed to N now. Now active node is N, active edge is 2 and active length is 1. So basically from N we have to select path Z, which is this, and move to that path by one location. So now I'm pointing to this Z. So this was the use of suffix link. From this Z going directly to this Z was like O1 operation for me. Okay, so that was the main optimization we are doing this from this algorithm. This algorithm is called Ukkonen's algorithm. Okay. So now I'll search for a dollar over here, which there's no dollar over here, and I'll create a node P dollar. Okay. Now, as I said, like this is the second node which is created in this phase. So I'll delete the layering link created from O to root, and I'll make sure that O points to P, so that in future, if there is a need to uh, jump from O, we'll jump to P directly for O of 1 jumping. Okay. So that will be one suffix link. And now I have created one node. So I'll just I have okay. Uh, okay, this is the second dollar I have added. First dollar was here. So this was already 3 and now it's 2. Okay. Uh, okay. And now P will point to P is the newest node and P will point to the root node. Uh, as of now, if any other node is created in this phase, then P will point to that node. Okay. Uh, oh, sorry, not P. My active node is N. N is pointing to root node. and P is also pointing to root node, but temporarily. So my active node was N, and I move to that suffix location, suffix link, which is root. So my active node converted to root, and now active edge and the length is still same. So now I'll move towards Z path, which is this path, by one location, and I'll reach here. I'll reach here. Okay. And again, I'll search for a dollar part, and there's no dollar, so I'll create another dollar path. And this is the third node that I've created, and let's call it Q. And then I can point this P to Q. And as I have incremented, added the, uh, okay, okay. Uh, as I have added another edge, I'll make this remaining as one. And now my present location, present active node was root. Okay, so what I'll do is I'll just decrement the length like we did whenever a came in. Okay, so now because our active length is 0, I'll just look for the dollar part starting from the root node, which is not there, so I'll add extra dollar part, and we are done with our suffix tree construction. Okay, so in okay, okay, yeah, this is the suffix tree for that. Okay, so starting from XYZ, the complete is here. Starting from the root node, coming here is the suffix starting from zeroth location, then suffix starting from first location. So we have all the suffix over here. So this is how our suffix tree will look like. Okay. So this is how we can create a suffix tree. And as our bookkeeping only involved different means executing each phase one by one, and in every phase the maximum backlog could have been just n. So these are just uh, main searching and traversing part can only be done n times, and all the remaining optimization are done in the bookkeeping. So all operations are of one. So we can actually create a suffix tree using this type of bookkeeping in just linear time. This algorithm is called Ukkonen's algorithm, and this is how we can solve the problem of such longest common substring and multiple similar problems using suffix tree by just using Ukkonen's algorithm. So that was all. Thank you.